Good day, pre-calculus students. We're turning the page to a new chapter. We're in chapter 3, polynomials and rational functions. Our lesson today is complex numbers from lesson 1. What's good about this lesson? A lot of it you may never have done before. If you even looked at a little bit of it, maybe it was a surface level. So maybe that it's new. Maybe you'll have a little more motivation to do it, only because you get to actually learn something that you have never done before. Let's get started. Here are your objectives. We're going to express square roots of a negative number as multiples of I, and we may have talked about that just a little bit. I'll just remind you. I believe at some point we talked about the square root of a negative 4 being not a real number. Your calculator will give you an error. That is because we know the square root of 4 is a 2, so 2 is part of the answer. But the square root of that negative 1 that's being multiplied by the 4, negative 1 times 4 is a negative 4, is I. So we addressed it once or twice, I don't know. So that's your first objective. Second bullet, plot complex numbers on a complex plane. This is very similar to a 3 dimensions. And we'll look at that in a few minutes. And then the operations of complex numbers. And so we haven't even defined a complex number. But complex numbers are not real. They have a piece of a real number in there, but then they have the other piece that has I in it. That's why it's made complex. We'll talk about that. So we're going to be adding and subtracting them, and we're going to be multiplying and dividing them. So the first page in your book just talks about complex numbers. And I don't really want to read this all to you. I'm going to glance through it and see, is there something in there that I like? It talks about the history of it a little bit. Talks about an algebra equation that you could not have solved. And what am I talking about? I'm talking about x squared plus 4 equals to 0. Before you've learned about complex numbers or imaginary numbers, you could not solve that. Because in reality, so what's going to happen? You would have to solve this for x squared. So if you move the 4 over to the other side, that gives you x squared now is equal to a negative 4. You're allowed to do that if you only have one term that has x's in it. And this x happens to be an x squared. So you're allowed to isolate it for x squared. But to solve this, you'd have to get rid of the square. That would be by squaring both sides, square rooting both sides. That's how you get rid of squared. So that works on the left side. Square root of x squared is x. However, we're stuck with the square root of a negative 4. And just a few minutes ago, I talked about that. You could not find that answer. And as a matter of fact, I got to be very careful. When you square root both sides, you actually introduce to yourself two possible answers, positive and negative. Positive and negative. Every time you square root both sides, you end up with two possible answers. One's positive, one's negative. But that's not the difficult thing. The difficult thing is there's a negative in there. Remember what I said a minute ago? Calculator won't give you the answer. Because x will be a 2i or whatever, a negative 2i, plus or minus. And so feel free to read more up on it here. So let's talk about what a complex number is. I'll read this part. We know how to find the square root of a non-negative. That means any positive real number, not not negative. In a similar way, we can find the square root of a negative number. The difference is that the root is not real. If the value in the radicand, that means underneath the square root symbol, is negative, the root is said to be an imaginary number. The imaginary number, I, is defined as the square root of a negative 1. So I'll just underline that because that's important. The square root of a negative number has an I in it because the square root of a negative 1, by definition, is the letter I. So a complex number, that's an imaginary number. This is called imaginary because there is no real number in there. It's just a plain I, pure imaginary. And I don't like how that's written, so I'm going to rewrite the word. It seemed okay a minute ago. Imaginary. Imaginary means just plain I. But a complex number is actually the best of both worlds because I have 5 plus 2i. 5 plus 2i. The 5 obviously is a real number. You can count it. 1, 2, 3, 4, 5. That's a real number. But 2i, you can't count it, on your fingers. It's not a real number. It's not real. It's imaginary. So you take a real number and add or subtract an imaginary number. We call that a complex number. Technically, that other answer I had before when I wrote 2i, that's just imaginary. But if you were to just be a little creative and say, my real number is 0 plus 2i, guess what? Now it became complex because 0 is a perfectly good real number. But who writes 0 plus something for fun? Nobody does. So you're never going to see 0 plus 2i and say that's a complex number. You're just going to see the 2i. Imaginary and complex numbers. So let's look at the textbook definition here. A complex is a number in the form of a plus bi. Can you take a guess what a is? A is the real number part. I hope you can tell that a has to be the real part. And b must be the imaginary part because it's going to have the I with it. Okay. If b is equal to 0, then a plus bi is just a plain real number because why? A plus 0i. Well, 0 times anything is just 0. So a plus 0 is just a. It's just a real number. That's what it means. If b was 0, then you just have a real number. If a is 0, we were talking about it, and b is not equal to 0, the complex number is called an imaginary number. Well, because if the 0 goes away, which it is an imaginary number. Notice what they said? The complex number is called an imaginary number. Can you remember what I said? 0 plus, I don't care what the number is, AI. I'm sorry, BI. Doesn't matter what B is. B could be 2, B could be 3. Yes, that's a complex number, but it boils down to just BI. Just a real number. It means just an imaginary number. That's what they're telling you. Similar to what I said to you. Now, how to, if we were given an imaginary number, how do we express it in standard form? Well, standard form is A plus the BI. That is standard form. And we like to put the real number first. Sort of like order of operations. Real numbers go first before the imaginary piece. So the secret is every time you see the square root of a negative number, think of it as the square root of that number times the square root of a negative 1. That way, by definition, the square root of negative 1 is I. So then I can write the square root of a times I. So like if I had, I'm doing an example before example 1. If I'm looking at the square root of negative 9i, negative 9, I'm sorry, square root of a negative 9. Pull out the negative number from the square root of 9 and call it the square root of a negative 1. And square root of negative 1 is I, so I say square root of 9 times I. And the square root of 9 is a 3, so that just turns into 3i. So that's how we get the negative out of a square root. So here's your first example. I just did it. I didn't even know I was doing this problem. I just did the square root of a negative 9. Wow. Guess it would help me to look for it. Let me just give you a new one then. Let's do the square root of a negative 144. So we know that's the same thing as the square root of 144. Whatever that is, times the square root of a negative 1. Because I'm pulling out the negative and putting it into its own square root. So that gives me, what is the square root of 144? I hope you know it's 12. 12 times 12 is 144. And what is the definition of the square root of a negative 1? I. So there's another example. I expect to see that in your notes. Since I did this one, okay, now you got another one. That was 2 for the price of 1. You need to get these examples in your notes. Those are actually more important than some of the stuff you guys write. Let's try this one. Oh, goodness gracious. I'm glad it's not the same one I've done. Express negative square root of negative 24 in standard form. Okay, so as I told you, a plus bi is standard form. So far, the first 2 examples and this one probably does not have an a component. That means a is 0. Reason is I don't see any number being added or subtracted to the square root of negative 24. But let's do this problem. As I told you, take out the square root of 24. Pull that out. You're left with a negative inside the square root. You're left with a negative inside the square root. But that can't be by itself, so that's a negative 1 inside the square root. Now, square root of 24 is going to be between 4 and 5. Now, how do I know that? Square root of 16 is 4. Square root of 25 is 5. 24 is in the middle of 16 and 25, and I happen to know my perfect square roots. If I list them all, 1, see how good we can do. 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144. Where do I get these numbers from? 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, 8 squared, 9 squared, 10 squared, 11 squared, 12 squared, and 169, then 196. And so it starts getting a little harder for me, and I think the next one is 225, I think. That's almost as far as I can go. Those are perfect squares. You should memorize those. Obviously, 24 is not in there. So the rule is break this apart into two numbers that do multiply to be 24, and one of those numbers happens to be one of those numbers I listed. Let's see. What goes into 24? Well, a 4 does, and 9 doesn't, 16 doesn't, obviously 25 doesn't, so I'm going to pick the 4. So I'm going to write that as the square root of 4 times the square root of the number that 4 times what is 24. I hope you see it that it's a 6. 4 times 6 is 24. Please do not forget the square root of a negative 1 is still there. Now, what is the square root of 4? It's a 2. So technically, the answer is going to be 2 square roots of 6 with a little I. Now, I don't know if that's how the book did it. That's how it should have done it. That's called simplifying a square root. We'll take a look and see. Well, that's a try it. That won't be in your book. You're just going to take my word for it. Now, what if somebody has said, "Sir, can I just leave it as square root of 24i?" Yes, it's the right answer. It's just not simplified. Simplified means that you have the smallest square root possible in there. Would I give you some credit? Yeah, I would. But you guys can do better. Okay, let's move on. Plotting complex numbers on the complex plane. This is hard in the sense it's hard to visualize it. That yellow line that you see is actually 3 dimensions. You need to picture it like this. You've got your y-axis, got your x-axis, and in reality, this is coming. Like I'm gonna pretend I'm looking at it from a different angle. It's actually coming out. It's 3 dimensions. So you can imagine how you could turn this back and forth if you were holding this object in your hand, and you could kind of get it to match up the way it looks right there. But either way, if you do it this way, you need to realize that the piece that came out at you is like coming out of the board, coming out of the page, poking you in the eye. It's coming out. That's what this is happening. It's actually coming out at you. This is coming out to you, but it's hard to visualize it. It's like 3 dimensions. And some people have done this before. Some have called this is your imaginary part right here. This is how many eyes you have, and this is your real part. So I can just put real, and then this part would be your eye part. So that part was your imaginary. Notice how they did it here. The real part is on the floor, and the imaginary part's up here. But when you put both of those together, you end up with the 3, which is the real part right here, and the 4i, which is right here. So I'm trying to visualize it coming out at you, so that's why I turned it around just so you can see. You'll have to just, I'm not going to spend a whole lot of time on it, but that's what it is. And so if we are going to try to do an example, you got to remember that if I draw something coming out, that's coming at you, or it's going into the paper. It's going that way. It's going inside. It's really hard to visualize it coming straight out, like an arrow coming out at your head. But that's basically how this axis will be. It's not really an XY axis because the real number looks like the X and the imaginary looks like the Y. But what are we trying to graph? Well, no, I don't see a problem there. I'm just, again, talking about the line that comes out. There's got to be looks like the same problem, same thing. I put the same thing twice, it looks like. Freebie. So how do you graph a complex number? You represent its components on the complex plane. Determine the real part, which the way they're drawing it would be your x-axis. That would be your real part. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the imaginary part looks like the y-axis. So as I go up, it's not 1, it's 1i. It's 2i. It's 3i, and so forth. 1i, 2i, 3i, 4i, 5i, 6i, all the way up. And so if your real number is positive, you know that we're talking about the piece that's coming towards you. But if the real part is negative, well, then your negative numbers are out here. So it's, oh, I didn't mean to erase. It's going to go, it's technically going into the paper. If your negative, it gets kind of complicated. Then what you do is you match up, like whatever the problem is, you match up the real part with the complex part, and just plot a point. That's all you're really doing. You're just plotting a point. You're not plotting a line. You're plotting a point. So, like if I was magically counting 1, 2, 3, 4, 5, 1, 2, 3, it's really a point. 5 plus 3i. It's a dot. It's not a line. But we realize that all the points could fall on this imaginary line in here. That's what's happening. They can fall on that line. But then there's others too. But let's see. We're going to get an example. Yeah, here's one. Okay. Wouldn't you know it? 3 minus 4i. We're just going to do the point. We're not going to graph a line. So here are my real number part. Here's my imaginary part. But the imaginary part is negative. So you would have to envision that the y's, see here's 1i, 2i, 3i, 4i, but I'm not going that way. I'm going down here. Negative I, negative 2i, negative 3i, negative 4i. And the real part is a 3, which we can do that easy. 1, 2, 3. So what I have to do, I got to go 3 to the right, basically, and counting 4 down. There's this dot out here. But remember, it's coming, it's like coming at you. It's in front of you. That's all we're going to do with complex. That's all the book had. Just plotting a dot. I probably won't. It's just something different. How do we add and subtract complex numbers? You heard of like terms. You add and subtract like terms. It's the same thing. So if you were adding two complex numbers, a plus bi, c plus di, if I said like terms, which of these terms are the same type? Well, a goes with c. So you can see why I would take a and I would add it to c. Those are your real numbers. Both of these are real. Now, the other two, these two are both the imaginary part. Imaginary. So I'm going to put bi plus di, bi plus di, but I have to put an I in front of them. After you add the b plus d, they get an I. Subtraction is very similar, but I need you to realize that this minus here has to be distributed. So technically, now I'm going to show you what they did on the right side. I have my a plus bi, but then I can say plus what? A negative c, a negative di. Now, when you put them together, the a goes with the negative c. So a plus a negative c is a minus c. The bi adds to the negative di. So you're going to get a b minus a d that you add first or subtract first, and then there's your little I on the outside. It's not that bad. Example. Let's add 3 minus 4i plus 2 plus 5i. I would write it like this, though. 3 minus 4i, adding 2 plus 5i. You know that the 3 has to add to the 2. That's a 5. But then you got to be careful. I don't know why I put that in a parenthesis there. If I'm just doing a shortcut and not doing all the put them in order, I should show that too, but I know the answer in the book they did, so I'll let you look at that. I need a negative 4i added to a 5i. So maybe I will do this. A negative 4i plus a 5i. Just that you can see that very clearly. The real number part was easy. 3 plus 2, 5, plus negative 4 plus 5 is a 1. So I can say plus 1i. But why do I put a 1 in front of things? We usually don't. We just say 5 plus I. And I think that's the answer. I'm going to run with it. Let's see what the author did. I didn't put the answer. You have to take my word for it. Sorry. I didn't put it in there. You can always look it up in the book yourself. Multiplying, by the way, I think your calculator actually adds imaginary numbers too. You can actually try that. Multiplying complex numbers. So it's really no different than multiplying anything else that are next to each other. In this example, they're multiplying a complex number just by a number 3. So you can see that I'm distributing the 3. So 3 times 6 is 18, and 3 times 2 is a 6, and don't forget there's an I. There's your answer. That isn't that exciting, okay? It's too easy. It's just to use the distributive property. Just don't forget to simplify if you can. We do have an example. And I know you guys can do this. 4 times 2i, 8i. 4 times 5i. What did I just do? What? I didn't mean to put the I. Let me back it up. Could erase my recording. 4 plus 2 is 8. Sorry about it. Plus 4 times 5 is 20i. Maybe I have an answer for this one, but I don't know. I added the try it with it, okay? Because that answer is never in the book anyway. So we'll check our answer, the a plus 20i, in just a moment. But let's just try this one. Beat me to the punch if you can. Negative 4 times the plane 2, negative 8. Now, when I say plus, be careful. It is plus. But remember, a negative times a positive is a negative. So it's plus a negative 24i. Most of the time, we don't write plus negative. We write negative 8. That becomes just a minus 24i. I'm just showing you if you brought down the plus, that's fine. Just make sure you know that negative gets multiplied by the 6, making a negative 24. So I think we can probably go and see what at least the example 4 was. Okay, I didn't put the answer for example 4, so I'm moving on. Next topic. Multiplying a complex numbers together. That's two complex numbers. So do you see how there is an a plus bi times a c plus di? Looks like a lot of work. I'm going to have to show you how to do it. It's FOIL. All they did was FOIL. So when we do an example, it's first, outer, inner, last. No different than what you already know. You just got to keep track of which ones have i's and which ones do not have i's in them. I don't want to do this generic problem, so I want to get to a problem right away, just because. But let's see how to do it. Exactly what I told you. Use the distributive property called FOIL. First, outer, inner, last. Here's an example. Example 5. Multiplying a complex number by a complex number. So let me see if I can make this one. First, 4 times 2 is your first. Do I need to write it out? 4 times 2? 4 times 2? 8. So I'm going to write that down, 8. That's my first. Next one is the outer. 4 times the negative 5, I. Don't forget the I. 4 times the negative 5, the negative 20. Negative 20. Don't forget the I. This was my outer. Next is my, let me label the outer. Outer. The next one are the two insides. Label those with an I. Inside. Now be careful, this is different. 3i times 2. It's reversed than what I've seen before. It's still going to be 3i times 2, and 2 times 3 is 6. So I'm going to see a 6i. So I'm over here, I'm going to write plus 6i. That came from the inner. Then, that's FOI, I need L for last. That means this last term of that binomial times this last term of that binomial. That's where the L comes from, FOIL. Now this is a 3i times a negative 5i. I'm just going to write that down for a minute. Plus, I said it was a 3i times a negative 5i. That's my last. Now, I have to teach you something. We're not done. Obviously, I have an 8. I have a minus 20i. I'll double check my work here. Yes. And I have a plus 6i. And I agree with that plus 6i. But now, and by the way, I know some of you are already saying, hey, can these two go together? Yes, I'll do it in the next step. But when you're multiplying I times I, that becomes I squared. So let me do the 3 times a negative 5. The 3 times a negative 5 is a negative 15. And the I times I is I squared. This is what you have to know. When you see I squared, it stands for a negative 1. And you might be wondering why. Well, remember what I is the square root of negative 1 times the square root of negative 1. That is I. This is I times I. So when you multiply two square roots together that are the same thing, it cancels out the square root. And you're just left with, because you can actually look at it like this. You can say, in one big radical, one big square root, you have a negative 1 times the negative 1. So the square root cancels out the square. If you think about it, square root of a negative 1 squared. The square root cancels the square, leaving a negative 1. So therefore, whenever you see I times I, that's an I squared, it equals to a negative 1. So this turns into a negative 1. So here I go. 8 minus a 14i, because negative 20 plus 6 is a negative 14. A negative 15, that's going to go plus a negative 15 in parentheses times a negative 1, because I squared is a negative 1. 8 minus 14i, negative times a negative is a positive 15. And if you look carefully, 8 plus 15 go together. My real number is 8 plus a 15. That's a 23 minus 14i. There's your real number. There's your imaginary part. That was a lot harder than anything we've done today. Let's see, what were the steps? Try this one. Okay, let's do this one. Again, first times first, 6. Outer, 9i. By the way, this is try it number 5. It should be labeled in your notes. Inner, negative 8i. Yes, and of course these two are going to go together. Last times last. Negative times a positive. I'm going to put a negative. 4 times 3 is 12. I times I is I squared. You know what that turns into. That's a negative 1. So it's 6 plus, why am I putting plus? 9 minus 8. They're like terms, is a 1i. Then I have a minus 12 times the negative 1. That becomes plus 12. The 6 and the 12 go together to make the real number 18 plus 1i, or just I. If you need more practice, I put some in the homework at the end of this section. You should practice them. I'll give you all the answers if anybody asks me. They did them. They want to check their answers. Let's move on. Oh, no. Is that the one I just did? I hope that's the answer I just had. 23 minus 14 sounds familiar. I was just looking at this right here. Looks familiar. Dividing complex numbers. Okay, we're getting a little harder, but we're almost done. We're almost done. Dividing complex numbers. We're going to introduce a word called a conjugate coming up here. You could read all this, but I'm going to show you instead. A conjugate is where you rewrite the same thing, but the symbol here switches. So if we're looking at 2 plus I times the square root of 5, and that's pretty standard to put the I in front of the square root. If it ever is written, you have a square root number times I. It looks funny to put the I on the right side because then it looks like the I could be in the square root. So you put the I on the front. But anyway, the conjugate is 2 minus I square root of 5. And since this one is the real number must be a 0 minus 1/2 I, the conjugate would be 0 plus 1/2 I, which we would just write as positive 1/2 I. Because I put the 0 on purpose so you would see that I did change that sign from negative to, I don't have a nothing there, so that means it's positive. That's complex. And why do I need to know that? I'm going to show you. If I repeated that for some odd reason, I'm not sure. Was that example? The example we had just done. Example 7. Dividing. So here's the problem. It really looks like this. 2 plus 5I, all divided by 4 minus an I. In order to do division of a complex number, there's a rule that says the denominator can never have an imaginary number. So by multiplying by the conjugate of the bottom, so let me repeat myself. I need the conjugate of the bottom, which will be the 4 plus the I. What do I do with it? Well, I take this top, I'm going to group it together, I'm going to group this together. I'm going to multiply both top and bottom by the conjugate of the bottom. 4 plus I over 4 plus I. Why is that legal? Because 4 plus I divided by 4 plus I is equal to 1. So all I'm doing is multiplying that by a 1, but it's a very creative one. Now, there's a lot of work here, okay? Because we got 2 binomials on top being multiplied and 2 binomials in the bottom being multiplied. There's 100 places for us to make a mistake, so I'm crossing my fingers that I don't make a mistake. So to do the top, I do first times first, 8I. I do the outers, 2 times an I, 2I. To do the inside, I do 5I times 4I. I'm sorry, 5I times 4. That's a 20I. Now I have the harder part. 5I, that's the last, times I. So you see how everything has been here? That this was my first, this was my outer, this was my inner, this is my last. So the last gives me 5I times I, wait for it, plus 5I squared. Now, do you realize 5i squared is just a negative 5? I hope you start seeing that. That when you have a 5i squared, that I squared becomes a negative 1 times a 5, so it just turns into a negative 5. I hope you see that. All divided by, got to do it again for the bottom. 4 times 4, 16. That's this one first. 4 times I is 4i. That's the outer. Look at the inside. Negative I times 4 is a negative 4i. Negative I times I is a negative I squared. Now, whenever you multiply by the conjugate of the bottom, it's because we're not allowed to keep an imaginary number in the bottom. But if you're very careful, you're going to notice that the bottom no longer has an I. Once I simplify, watch this. 8i. That wasn't an 8i, was it? How come nobody stopped me? It's not an AI. It's just an 8. I just saw it when I looked at the 2 times 4. Sorry, guys. I'm glad I caught it. 8. Or else I'd have to give extra credit to somebody. 2i plus 2i is 20i. 2i plus 20i is 22i. 5i squared is a minus 5. Over. Now watch it. Told you what's going to happen. The bottom. I's are all going away. Because 16, bring that down, 4i minus 4i cancels. Bubba, it's gone. No more i's. Oh, I know what you're thinking. But there's a minus I squared. But a minus I squared means that I squared is a negative 1. Think about it. I squared is a negative 1 times a negative becomes a plus 1. That's like hocus pocus. It's magic. No more do I have i's in the bottom. Can I simplify the top better? Sure, I think I can. 8 minus 5, the real number part becomes a 3, plus 22i. The bottom becomes 16 plus 1, that's a 17. So I just do the whole thing divided by 17. Now, I don't mind this answer, but there's a good chance that the textbook and the mom assignment will write it as 2 fractions. In other words, they say the 3, the real part is 3 divided by 17. And then the imaginary part is 22i divided by 17. So you can put the 17 under the 22. So there you go. Do this problem 3 times. If you get the same answer 3 times, then you know you're doing something right, assuming I'm right. I'm sure you'll let me know if I'm not. Let's go see if we have some solutions this time. This was a solution for example 6. Let's see, I have it written down there. You can check it. My first glance says I think I'm right, both A and B. And then the other one is that hard one that we just did, example 7. So they have a lot of steps. Feel free to enjoy those steps. You might like it better than what I did. And I'm looking at the answer, and it sure looks like what I think it is. I think I'm right. Oh, happy day. Example 8. This is not really a problem that I've run across in any mathematics, but I understand why. I mean, yes, it does come up when you're trying to do something later, but substitute a complex number into a polynomial. So polynomial means more than one term, and so there it is. F of x is a quadratic. Okay, it's x squared minus 5x plus 2. And we are evaluating the function when we're plugging in a 3 plus I in place of what? I hope you remember from before that this is all this gets plugged into the x here and the x here. That's the concept. That whole thing, 3 plus I, goes into both. So I'm going to write it out. F of 3 plus I is going to be equal to something being squared. What squared? 3 plus I. 3 plus I all squared. Minus 5 times what? Minus 5 times 3 plus I. Plus 2. That's just a plus 2 minding his own business, not bothering anybody. Plus 2. So now we have to simplify. And 3 plus I squared really means 3 plus I times 3 plus I. That means you're using FOIL. So 3 times 3 is 9. 3 times I is 3I. I times 3 is still 3I, reversing the order. I times I is I squared. Then the next part, I just did all that right up to here. Now I got to distribute this minus 15, 5 times 3, minus 5 times I is minus 5I. And bring down the plus 2. What a gobbledygook of mess. Here goes. Okay, let me go check my pen. We'll do the real numbers first. 9 minus 15 is a negative 6. Oh, I should also remember that, I should break this down a little more here. Let me do this. 9, before I do that, 9 plus 3 plus 3i is 6i, plus I squared is plus a negative 1, so minus 1. Bring down my minus 15. Bring down my minus 5i. Bring down my plus 2. Okay, let's try this again. I will do my real numbers first. 9 minus 1 is 8. 8 minus 15 is a negative 7. Negative 7 plus 2 is a negative 5. Okay, there's my negative 5. Now I'm going to do the imaginary pieces. 6i, that's positive, minus 5i means I only have one I left, plus I. Negative 5 plus I believe is the correct answer. If not, I'll be bummed. Let's check the author. Okay, there's the same problem. There's all the work, and lo and behold, negative 5 plus I. I believe that's what I had. Same problem. This is the example 8. A lot of steps there, and I'm going to concentrate on the negative 5 plus I do believe, my marker here, I do believe was the answer. Hope so. You'll let me know if I'm not right. Okay. Let's drop down to try it number 6. These should be in your notes. There's no reason these are not in your notes. F of x, we're doing another, there's another one just where we're substituting a complex number in. And you might be wondering, why would we ever plug a complex number in place of x? Well, your some functions, their roots are complex. They're not crossing the x-axis. I'm just telling you, coming up, we're going to figure out that that is a possibility where our zeros, our solutions are complex. So that's what's happening. All right, so let me see if I can bring that down a little bit. Oh, I made it too small. F of, I'm plugging in 8 minus I. This is a try it. So in reality, you should do it first and pause the video and do it first and see if you get it right. I'm doing them with you because they're complicated. So that turns into, if I plug in all of this in place of x, that's a 2x squared, so it becomes a 2. What's being squared? My x is 8 minus I, so it's 8 minus an I. That part's being squared. Not the 2, just the 8 minus I. Minus 3 times x, so it's minus a 3 times the 8 minus I. And then that's it. Okay, so just like before, the 2's on the outside, but now I have an 8 minus an I times an 8 minus an I. And this piece is real easy. It's a negative 3 times 8. That's a negative 24. And then a negative 3 times the negative I. The negatives cancel. Just gives me a plus 3i. So I did that already, okay? But now I just got to FOIL this 8 minus I times 8 minus I. So equals to a 2 times 8 times 8, 64. 8 times a negative I, negative 8i. Negative I times 8 also is a negative 8i. Negative I times negative I becomes positive what? Positive I squared. Then, that's all I did was multiply 8 minus I times 8 minus I. Now I bring down my minus 24, bring down my plus 3i, and the reason this is in parentheses is because there's a 2 in front. Now I can distribute it now, or I could simplify the inside now. It's up to you. I think I'm going to distribute right now, then I'm going to simplify. Equals to 2 times 64 is 128. 2 times a negative 8 is a negative 16. Don't forget the I, and that's going to give me another negative 16i. And then a 2 times an I squared is plus 2i squared. So see, now I can remove those parentheses because I multiplied it through by a 2. Bring down my negative 24 and my plus 3i. Okay, just like I did before. Concentrate on my real numbers. 128. That's a little bigger than the other one was. Well, I should simplify. Equals to 128. This turns into a negative 32i. This I squared becomes a negative 1 times 2 minus 2. Then I have my minus 24. Then I have my plus 3i. That was probably better to do that first than what I was going to do, but here goes. 128 minus 2 gives me 126. 126 minus 24, I think, is 102. Okay, I'm going to write it down, 102. Now I have a negative 32i. I'm being added to 6i, which means 6 away from 32, and the answer has to be negative. Question is, negative what? Negative 26? I? So if all is fair in the world, then that would be my answer, 102 minus 26i. So think about that for a minute. This was a try it, so I don't have a solution for you. You're going to have to take my word or do it a couple times and see if you disagree with me. This is where you'll earn your points, I'll tell you that. You find my mistake, if I have one. Example 8. I don't know if I want to do this one or not. I'm going to do it until I don't want to. Nope. Excuse me. Substitute a measure number in a rational function. Well, at least we're only substituting a rational number. We're not substituting a complex number. That's good. We are plugging in a 10i into everywhere we see an x. So it's not any different than what we've done in the other, just it should be a little easier, at least somewhat. F of 10i will equal to, now the numerator is 2 plus x, so it's going to be a 2 plus the 10i over, now the x is first. That becomes a 10i plus 3. 10i plus 3. Da-da! It's simplified. It's substituted in. But it's not simplified. Why? First of all, you're never allowed to leave an I in the denominator. So this is the job for the conjugate. Multiplying the top and the bottom by the conjugate of the bottom. Just change this plus to a minus. Here goes. Times 10i minus 3 over 10i minus 3. So let's distribute. Use FOIL on the top. Equals to first times first, 20i. That's first times first. Outers, 2 times a negative 3 is a negative 6. Inner is plus 10i times 10i is a positive 100i squared. If you don't like how I wrote that, I'll try to make my zeros a little more 0i squared. That's first, outer, inner. Last is 10i times the 3, negative 30i. All of that divided by, again, first times first, 10i times 10i is 100i squared. Outer, 10i times a negative 3, that is a negative 3, negative 30i. Inner, a positive 3 times 10i, positive 30i. Last times last, a positive 3 times a negative 3. That's a negative 9. Oh, my goodness. Equals Real numbers. Let's see. The only real number I see in the top is this right here. These two. Because it's a negative 6 minus 100 because the I squared is negative. So that gives me a negative 6 minus negative 106. Then I have 20 i's combining with a negative 30i, negative 10i. Then the bottom. I have the bottom as, let's see, 100i squared is the same thing as a negative 100. Negative 30i cancels out 30i's, which is what I wanted to happen, minus 9. Now all that equals to, well, the top doesn't change unless I wanted to cancel out the negatives somehow. Let's see, would I do that? You don't have to. The bottom becomes a negative 109. Since there's a lot of negatives, you could cancel out all the negatives. I like this answer. To be totally honest with you, I don't see why I would play with it, but I have a gut feeling that this is probably what the author's going to do. They're probably going to say, hey, those two, this has negative, that has negative. You could factor the negative out, leaving 106 plus 10i. Why am I thinking that? Because the bottom has a negative also of at 109. So the negatives technically cancel out. When you see everything with a negative answer, I could see that they would pull that out. Equals to a positive 106 plus 10i, all of it divided by 109. And then remember what we said? We could create that as two different fractions. That 109 becomes a denominator twice. 106 over 109, there's your real part, plus 10 over 109i. That's very common. So my guess is they're probably going to give, maybe they gave me this answer up here. It's what I just got up here, but I can see all those negatives. We'd have to just check it and see. Let's go look. Well, okay, look at all their steps. It's in there. I'm going to go all the way to the bottom. There it is. Sure enough. Maybe they had a different order, but same answer. And now, after that, we do have a try it. I really would want you to do that. But this one isn't so bad. You're just plugging in a negative I. So let's just, you should pause the video. Do it yourself. It's better for you to find your errors. But nonetheless, here goes. F of a negative I should be that means X will be, this X and this X has to be a negative I. So negative I plus 1 over a negative I minus 4. Just like before, no i's allowed at the bottom. So we got to multiply top by the conjugate of the bottom, which means this minus just becomes a plus. Negative I plus 4 over negative I plus 4, grouping that together so we could use FOIL, is negative I times negative I is a positive I squared. First times first. Negative I times 4 is a negative 4i. A 1 times a negative I, negative I. A 1 times a 4 is a 4. All over. Now remember, I'll know I'm right if the bottom loses all i's. If it doesn't lose all i's, I made a mistake. So negative I times negative I is a positive I squared. A negative I times a 4 is a negative 4I. And then the negative 4 times a negative I is a positive 4I. And then the last two terms, negative times a positive is a negative, 4 times 4 is 16. So it's a positive 16. Let's see what happens here. I squared becomes a negative 1. A negative 4I minus an I, there's like having a 1 there, negative 5I, plus 4. I don't know why I didn't use that already, but there it is. I'll simplify it again in a second. The bottom, I squared means a negative 1. Negative 4I plus 4I cancels. Very good. Plus a 16. Plus a 16. So that turns into this negative 1 and a 4 becomes a 3 minus 5I. And the bottom becomes looks to me like a 15. So if I do the same trick and write the 3 out of 15 minus a 5 out of 15I, the first fraction doesn't reduce. Oh, yes, it does. 3 goes into 15 5 times. That becomes, becomes a 1/5. And 5 goes into 15 3 times. So it's minus 1/3 I. Wow. That was a try it. I don't have any way to check that answer, but it looks nice. Moving on. Okay. Powers of I. Powers of I means i's that have exponents. So we already can figure out that an I to the first is just an I. I to the second, we already learned was I times I, and I times I is a negative 1. We've learned that. So I cubed means I'm just adding one more I. So I, and we've already learned that I times I is a negative 1. So negative 1 times I has to be a negative I. And that's sure enough, that's what I have. Now, if you go to the fourth one, I, you've learned that an I times I is a negative 1, and an I times I is a negative 1. So negative 1 times negative 1 should just be a plain 1. Let's see if it is. After all this work, plain 1. So what happens in the fifth one is the same answer as the beginning. So what I'm saying is this. It's a pattern of 4. I, negative 1, negative I, and then we have a positive 1 is their last one. So if I say this is I to the first, this is I to the fourth, then this is I to the fifth, and this has to be I to the 8. So you can see in the middle there, I have 6 and 7 here. I to the 7, I to the 6th has to line up here. Every 4. Now, the computations are all in there, and you can play that game. Let me just give you an example. Look what happens when you have I to the 5th. If you know that groups of 4 are important, and I take the exponent 5, and I divide it by 4, We know 4 goes into 5 one time, but I don't care about that. What's the remainder? 1. So that puts us at the beginning of the pattern. Because at the end of 4, we were here, right? A 1. So 1 more puts me at in this spot, which gives me the same answer as I. I to the 5th should be I. Let's do I to the 7th. I to the 7th. All I really care about is if I take 7 divided by 4. Again, I get through one full pattern. And that's 1 times 4 is 4. If I subtract it, there's 3. There's 3 more then. I haven't finished another pattern. So what would be the third one be? Third one would be 1, 2, 3. It would have to be a negative 1. A negative I. So let's look at I to the 7. I to the 7 is negative I. Negative I. I don't know what I said. Negative 1 is here. If I said negative 1, I apologize, but it's a negative I. So why is this method pretty powerful? Because look at the example here. I want to do I to the 35. Well, I don't want to list them all. I mean, I don't want to keep doing I, negative 1, a negative I, a 1. That's 4. 5, 6, 7, 8. Well, I got to keep on going. 9, 10, 11, 12. I got to go to 35. Do you want to keep doing that game? You can. It works. It does work. But why don't we just take 35, take away the full set of 4, which would take me this whole set of 4. How many of those do I have? 4 goes into 34. 8 times 4 is 32. 9 times 4 is 36. So it has to be 8 times. So it's all 4, all 4, all 4, all 4, all 8 times. So I don't care about the 8. I care about 8 times 4 is 32. And when I subtract, I have 3 left over. What does that tell me? After you've done this 8 times, you're 1, 2, 3. You're at a negative I. That should be the answer, negative I. That's my thought. You could list them all and just keep going. You could start from the top and say, I just go, I, negative 1, negative I, 1. I, negative 1, negative I, 1. I, negative 1, negative I, 1. And see how far we got so far. 1, 2, 3, 4, 5, 6, 7, 8, 12. You got a long way to go if you want to do it that way. Or look at the pattern. You could do all the algebra. You could do all the algebra and factor out all the i's and I squares and do that. You can do that. Let's check it to see if I'm right. I could be even wrong. I think the answer is a negative I based on dividing by a 4 and look for the remainder. The answer. Sorry. I hope it is. Because that takes me to the end. Whoop, I didn't. And yeah, there's the homework pages. You should be doing your homework. Goes in your binder. Most likely this week I'm picking up a homework, or at least having you submit it. So get it done. And I've given you all the problems, even in here. You don't have to go look in the book if you don't want to. There they are. The finish is up there, I think. Yep, that's, well, is that a last page right there? All right. Take me back to the beginning here. I'll stop right there. Do them. Over and out.